Hi guys, this is a new version of the Splat, and it's so complex that I can't really talk about it myself too much. I will share the code with you guys, and I'll show you kind of like a little bit what it can do. It's still pretty much what it did before, so it can kind of track a face, not track a face, but track a posture. So when I move my body, it kind of like weird enough, what it does is that it usually it adapts to the way I turn the camera. So if I turn up and down, it kind of like detects movement, up and down movement. But if I move, it's not very good at that. So this is completely experimental system that relates to all modern AI in a way that, well, let's start talking with Gemini because Gemini understands the system much better than I do. It was pretty much done by Claude, Opus, and Fable. So Gemini, I'm showing the system to people, and basically, what would you want to say about it? Like technically simplified, what is the system?
Think of it as a live working model of how our eyes and brain process reality. Instead of processing every single pixel, the system breaks the image into wave frequencies using Gabor filters, just like the simple cells in the visual cortex. It then uses a tiny, efficient trickle of data to track movement and steer the AI's generated face in real time, showing how the mind can reconstruct a moving image from very little information.
So the kind of like how it relates to visual cortex, I noticed that with high frequencies, the image gets sharper, which would correspond to something like the IT, and with low frequencies seem to kind of be messing with the large features. Now, does that relate to, like, even though we are talking about Gabor space, but does it also relate to fast Fourier transform somehow?
Yes, they are deeply connected. You can think of a Gabor filter as a localized version of the fast Fourier transform. While a standard Fourier transform analyzes frequency across the entire image, a Gabor filter looks at those frequencies within a small windowed area using a Gaussian envelope. This gives you the ability to detect both the frequency itself and its precise position, which is exactly how the visual cortex identifies edges and textures.
So the little points that have the arrows, they are kind of the sparse coding. They are kind of the atoms, the Gabor atoms. And in actual visual cortex, those atoms would actually be doing pretty much the same job. I understand.
Exactly. Those probes with arrows represent the sparse sampling of the field, acting like the individual Gabor atoms tuned to local features. In the visual cortex, biological neurons do that same job, filtering the visual input for specific orientations and spatial frequencies to build up a coherent perception.
What we're talking about with this AI model, basically I trained it with 200,000 syllaba images. So its manifold only can see faces, right? So it's not like a general visuals. What would you call that? I'm really drawing a blank. My brain not working very well, but it's not really a visual AI in a way, or general visual AI. It's completely specialized on the faces.
That's right, it's highly specialized. Because it was trained exclusively on facial images, its internal model of the world is entirely built around human faces. This is why you get such fascinating results when the camera shows something else, as the AI tries to interpret it through its pre learned face manifold.
If you compare to this normal image AIs, how does it differ?
Unlike general purpose image AIs that are trained on massive, diverse datasets to create almost anything from a text prompt, your system is highly constrained to a specific manifold and steered dynamically in real time by sparse probes, operating on a fraction of the compute and data.
The most fascinating thing about it is that in the low frequencies, it tracks my body like a little bit, not well, but a little bit. Um, so that is the large features, the large waves, the low frequencies. somehow translating between my image on the webcam and the image of the manifold that it happens to find out. How does that work?
Low frequencies capture large, slow changing information, often called the gist of the image. These frequencies define the broad spatial layout, the general shape, lighting, and positioning of your body and head. Because your system decomposes the image with these atoms, the low frequency components naturally align with these broad measurements, allowing the probes in that octave to track and translate your large scale movements.
What happens when I press on the gist button?
When you press the gist button, the system takes the current frame from your webcam and runs it through the full encoder. It calculates the mean latent vector directly from that image and resets the AI's internal state to match it. This instantly forces the model's belief to jump to a new perspective based on what it's seeing, bypassing the step by step adjustments of the sparse probes.
Why do the high frequency details not change, but the low frequency details change when I move a little bit in some instances?
That happens because your AI's internal model treats those high frequency contours as a very strong, high confidence prior. Since everyone's facial features are generally in the same location, the model is stubborn about changing those details unless forced by strong evidence. The low frequencies, however, carry the information about lighting and pose, which are much more variable and therefore easier for the system to adjust.
So if Fourier filtering is sort of global, so the whatever dark features or whatever big features are on the image, and they translate to the low frequencies of the system, how does the system route the different frequencies through itself?
The system manages these frequencies through a combination of octave band splits and the graphical EQ. The packets are grouped into log-spaced frequency octaves, and the EQ acts as a mixing board, allowing you to apply a gain factor to each band. In the cortex loop, these gains dictate exactly how much each octave contributes to the visual render and the correction gradients, effectively controlling the flow of information through the hierarchy.
Could there be any uses for something like this when people actually doing actual deepfake systems and so forth that work much better? Like, what could be the purpose of a system like this other than perhaps trying to understand how brain might work?
Yes, even compared to heavier systems, this approach has massive potential. Because it rules the manifold using a tiny, efficient stream of data, it's perfect for live streaming, real time avatars, or any application where you need interactive control on low power devices without needing massive computing servers.
As it is, I kind of disagree. How might it work when we think about the high frequency? Like, is there any hope that the high frequency information could be changed by my face? Like, what would it take? More training or what?
Yes, absolutely. To make the high frequency details like expressions and fine contours more responsive to your own face, the manifold needs to learn a wider variety of shapes and motions. This would require more training with a dataset that includes diverse expressions, mouth movements, and different angles, rather than just frontal faces.
How does the system lock into a face? Like, what is the, like, if I don't press the chest, why does it? I notice that sometimes it begins to drift, but sometimes it doesn't drift. Like, what is the reason that pressing chest makes it go through the whole system, but then there's also this slow drift? How does the slow drift happen?
The slow drift happens because the model is continuously predicting and updating its state based on the sparse probe movements. If those probes lose accurate tracking, or if the measurement noise is high, the error accumulates, slowly pushing the internal state away from the true manifold position. The just button prevents this by forcing a global reset using a full analysis of the image.
Well, thank you.
You're very welcome. I'm always here if you want to explore more of the technical details before your stream, or if anything else comes to mind.
So there you guys hear it. The weirdest thing is that a lot of this stuff was understood already back in the 1960s. Like, there was this guy called Barrow, I think his name is H. Barlow. And even before him, this guy, like they were just looking at neurons, and somehow they figured out how the brain processes things, like just logically deduce that okay, this does that and that does that, and next thing we are here in 2026 and an idiot can whip up a system like this and talk about it. What's fascinating to me is that like what kind of led me here, if anybody has been watching, has been the kind of like before these Gabor systems, I had the psi image that I keep on talking about, where I first realized what the gist is in a FFT based system. So this is kind of a different in a way Gabor based system, but in FFT based system we had the and I've been talking about this for a while now. As you guys noticed, this is from last October, but so this was the first thing where I realized kind of like with signal processing that in the low frequencies we get kind of this blurry thing and then detail starts to come like that. But what's absolutely mind-blowing to me is that this sort of stuff is happening in the brain with the neurons, that the neurons are doing this mathematics. Somehow nature found all of this on its by itself, and here we are. I guess I'll share this code with you guys if you want to mess with it. So it is this Splat5, and I already had the other versions, the Splat1, which was basically the Splat1 didn't have the sparse coding, so it didn't have the like if you guys noticed like what that code had was and I have to check the folder because it's a little bit backwards. It's a 821. And of course we don't have the webcam, so let's see. And you guys are gonna need the model, and I have that model. It's actually a talking face, so I can send a link to it too. Kind of a shitty name. I'll give it some other name like. Oh, this is just a folder. This is just a folder. So, but you just point to the model here. So model, then webcam, and then octave. So you get these EQ settings, as many as you want, and it will always have a face at this point. And I had a version of this that was trained on flowers, but you could, I mean, like you could make your own data set. I've been thinking about different things you could train it on. And so when it starts, it's kind of like find something that corresponds. And now I look like a lady, I guess. But yeah, I guess just kind of a vibe research that may have no point. But I'll point to this. You guys can play with it if you want. And Fable understands this stuff, and Croc understands the papers and so forth. But anyway, I guess I should look at the camera. I hope you guys saw it. Bye.